Good morning and welcome everybody to this morning session, which is the last session of this conference. Our first speaker today is Lasse Rempe, who is going to talk about a counterexample to Eremenko conjecture. Please.
Dear organizers, thank you all for this most generous invitation to gather in a lecture hall and speak of complex iteration. What a strange few years it's been to sit with a computer screen instead of in a lecture room and follow talks held over Zoom. Thus, it has been a joyous pleasure to meet in such a pleasant place and to again speak face to face of Julia sets and Hausdorff measure. This week, we've learned of many things, of Siegel disks, of Hermann rings, of beta numbers, of logarithmic convexity, of Julia sets and their geometric complexity. Now, I shall speak within my lecture about an interesting conjecture of Eremenko from a fine paper of 1989. He asked if each escaping point can to infinity be joined using a connected shape, all points of which themselves escape. Although quite simple, it appears, this question has for many years caused me and others some despair, sleepless nights, and graying hair. Through our intense investigation of transcendental iteration, much progress was indeed obtained, but the conjecture, it remained till now. By work with Waterman and Martí-Pete, now we can describe to you within my lecture a counterexample to Eremenko's conjecture. I'm afraid the rest of my talk will be in prose. But no, it's great to be back here. And it was 2013, I think I was last year for Eremenko's 60th birthday conference. And I came up with some rhymes then as well, because I know that he likes that sort of thing. So it feels nice to be here. And I've given this talk before, so I apologize to those who've maybe heard it online, but maybe not everyone has. And it's also just nice to be able to talk about it in person here. So I hope you don't mind. So let me elaborate a little bit on my abstract that I just gave you. If I can, let's see. Will I be able to? There we go. So I mentioned this fine paper of 1989. So this is a paper of Alex Eremenko on the iteration of entire functions from 1989. And in this paper, he studied what we call the escaping set. So this, I realize, is the first talk on transcendental dynamics in this conference, which is somewhat unusual these days. So what is the escaping set? Well, so we start with the transcendental entire function, so just an analytic self-map of the complex plane, which is not a polynomial. And we look at the set of points that tend to infinity under iteration. So it's in a sense the analog of the basin of infinity of a polynomial that we've seen in many of the talks already. So Eremenko was the first to study this set in general, and he proved a number of general results. So in particular, he showed that the escaping set is always non-empty. There always are such points that tend to infinity under iteration. And he also proved that when you take the escaping set, you take its closure, then every connected component of that is unbounded. Well, this is essentially the maximum modulus principle. So the hard part is showing that the escaping set is indeed non-empty. And in the intervening years, and certainly over the past 2 decades, the study of the escaping set has been, I would say, a central part of progress in transcendental dynamics. So why would we be studying the escaping set? Well, for polynomials, as I already said, we have a nice open set, right, of points that converge to infinity under iteration. This set is foliated by what we call external rays, where we've seen them a lot already. If you don't know what they are, it doesn't really matter. But these external rays have been used to great success in polynomial dynamics to understand what goes on in the dynamical plane. And in particular, they've been used for these puzzle techniques first introduced by Yorkos, which have driven so much progress and which we've heard a lot about in the past few days. Now, when f is transcendental, the set is not quite as nice, right? So it's certainly no longer open. It is, by definition, if you write down the definition, you can work out that it's an F sigma delta. So in other words, it is a countable intersection of countable union, of countable unions of closed sets. It turns out it's never really better than that. So it's never, for example, an F sigma set, never a countable union of closed sets. That's something I proved very recently. It was a question of Phil Rippon. But nonetheless, so even though the set is complicated, and you will see this, that because the set is topologically complicated, some things can be counterintuitive. But anyway, despite the fact that it is complicated topologically, it often contains very useful structures, such as curves to infinity. We had these dynamic rays for polynomials. Well, we have such curves as well for many entire functions. So here's a picture of one of those. And having these curves gives structure to the dynamical plane. And they've been used to some success to understand the dynamics. So the general goal is understand the dynamics of F by understanding the structure of the escape. And I'll talk a little bit more. I'll give a bit more background, and I'll try to mention with some of these results how they've influenced the field. But let me mention now Eremenko's conjecture. So Eremenko's conjecture is simply the question whether the result that I stated at the beginning, every component of the closure of the escaping set is unbounded, can be improved to say that every component of the escaping set itself is unbounded. So Eremenko wrote in his paper, it is plausible that the set I of F has no bounded connected components, or as I've already heard, I like to phrase it, it seems that each escaping point can to infinity be joined using a connected shape, all points of which themselves escape. Or yet, in another way, Eremenko's conjecture is the conjecture that every connected component of the escaping set is unbounded. That's the question. It's quite simple to state, and it's turned out not to be quite so simple to study. So let me start with a theme and variations on Eremenko's conjecture. So a number of variants of Eremenko's conjecture have also been studied over the years and have been resolved. So variation one, the first one that was resolved, is that instead of asking whether every connected component is unbounded, let's be a little bit less ambitious, and let's ask whether there is any unbounded connected component of the escaping set. And this has been answered in the positive by Rippon and Stallard in 2005. This was a very, very influential paper. It's called On Questions of Fatou and Eremenko. They didn't introduce the fast escaping set, but the fast escaping set had been used as a tool by Bergweiler and Hinkanen, but they realized its fundamental importance in transcendental dynamics. So I won't define what the fast escaping set is because we don't need to know. But there is this subset of the escaping set. It is NF sigma. It has nicer topological properties. For it, Eremenko's conjecture holds. And it's been extremely influential over the past almost 20 years that we've known about it, not only in transcendental dynamics, but also in quasi-regular dynamics, where it's really kind of given rise to the notion that we can study quasi-regular maps, which are not uniformly quasi-regular, with tools inspired by complex dynamics. So here's a second variant, right? Instead of asking, is every connected component unbounded, we can ask, is the union of the set with infinity connected? Now, those two things sound very similar, and they are equivalent if the set is closed. If the set is not closed, they're actually quite different. This one is quite a lot weaker, but it has the advantage that it was proved to be correct. So it's known that when you add infinity to the escaping set, you get a connected space. Okay, so this may seem quite close to Eremenko's conjecture, but it may be worth keeping in mind that there are spaces where every connected component is a point, and yet when you add one more point, they are connected. It's called an explosion point. So, okay, so this does not resolve Eremenko's conjecture. In the other direction, so these were weaker versions of Eremenko's conjecture. There are also stronger versions of Eremenko's conjecture. The first one posed by Alex himself. In the same paper, he suggested it would be plausible that, in fact, the escaping set union infinity is path connected, so that every point can be joined to infinity by a curve. And this turned out to be false. So this we answered in 2011 in this paper with Günther Rottenfußer, Johannes Rückert, and Dirk Schleicher, where we showed it's true for quite a large class of functions, but it's not true in general. So we constructed an example of an entire function where the Julia set, so the Julia set union infinity is always connected, but in our example, it actually contains no curves at all. So it's it's a continuum that contains no arcs whatsoever, in particular, no arcs to infinity. And again, to answer this question and then further study this question has required quite a lot of progress on what we call the Eremenko-Lubitsch class. I mean, one of the things that was inspired by this, a question that came up once we had this example, was whether this example could be realized with only finitely many singular values. Now, again, by singular values, they're the generalizations of critical values. And Chris Bishop, in the end, was able to show that, yes, this can be done. And he had to develop a very powerful technique of quasi-conformal folding, which, again, has been hugely influential in the field. Final version that I'm going to mention, final variation, is what we might call the uniform version of Eremenko's conjecture. So this was also suggested by Alex, but not in print. He mentioned this to me at one point when we were sitting in a cafe in Liverpool. So he suggested that if you have a point in the escaping set, and there could be an unbounded connected set, such that the iterates converge to infinity uniformly. And of course, it would be nice to have that, because then when you have this uniformity of escape, you have a chance to do something with it. And it also turns out that this is false. So there are, again, entire functions where you can, in fact, connect every point to infinity. At some point, you can connect to infinity, even with a curve, some escaping point. You can connect to infinity with a curve of escaping point, but this curve does not escape uniformly. So the point goes to infinity, every point on the curve goes to infinity, but not with a uniform speed. So what do we conclude from this? What we conclude from this, it's at this stage, it's not quite so clear what answer we should expect, right? Because some weaker versions of Eremenko's conjecture are true, and some stronger versions are false. Well, what about Eremenko's conjecture in itself? Well, there are many situations where it is known to hold. So, for example, if the post-singular set iterates of these singular values remains bounded, that's a situation where I was able to show Eremenko's conjecture always holds. Then in the same paper I mentioned before, if the singular set of F is bounded and F has finite order, this conjecture is also true. There are some other very different situations where which Phil Rippon and Gunnar Stallett studied, such as when there's a multiply connected component, which again we might think of as a strange situation, really, that this multiply connected component of the Fatou set, which we all know what the Fatou set is, but in this case we can just call the Fatou set the complement of the boundary of the escaping set. Functions which have small order and quite regular growth, functions of order less than 1/2 with only negative roots, functions of very small growth. So there are all these classes where we do know that Eremenko's conjecture holds, but in general it remained open. And the challenge in trying to resolve the conjecture, well, they're really twofold. So the first question is, what could such a counterexample look like? So we know that we know that there are these unbounded components in the escaping set, and they're going to be dense in the escaping set. We know that the escaping set together with infinity is connected. So we can't have something, which is just like a bounded component somewhere, sits somewhere and surrounded by something else. This can never happen. So probably one would have to have a situation where we have maybe this kind of curve that we talked about before. We have an escaping point, and we have maybe a curve on which the points go to infinity, or maybe not, who knows? And then somehow we have to be able to separate it out with something which is not in the escaping set, but then this point has to be accumulated on by some unbounded component. So that's one challenge, figure out exactly what would the counterexample look like. But even if we get that, for a long time it really wasn't clear how would we obtain enough control to be able to make such a counterexample. So, if you'd asked me, before this year, I would have said, I think Eremenko's conjecture is false, probably. But how I wouldn't have been able to tell you how would we get this kind of control. But then this January, coming from work on a very different topic, James, David, and I realized that we could actually make a counterexample. So we could solve both problems and make a counterexample to Eremenko's conjecture. In fact, there exists a transcendental entire function such that the escaping set has a component that consists of just one point. Right, so in particular, it is bound. And that is what I would like to talk about. Okay. So as I said, this actually came out of work on a different topic, and that's the topic of wandering domains, on which David will say more in the next talk. So please do stay for that one. It's a general saying that if you give a talk, you should define all the terms in its title. I'm not sure whether this applies to conferences, but I'm not sure whether we've had the definition of the Julia set in this conference on geometric complexity of Julia sets. Certainly, we haven't defined it for transcendental entire functions. So let me just remind you that if we have a transcendental entire function, the definition of the Fatou set and the Julia set are the same as they are for rational maps and polynomials. The Fatou set is the set of normality, and the Julia set is the set of non-normality. In other words, the place where we have chaotic dynamics. And the Julia set is also the boundary of the escaping set. Before. So what is a wandering domain? A wandering domain is a connected component of the Fatou set that is not eventually periodic. Domain doesn't come back to itself at any point. It's not a Ziegler disk. It's not an attracting basin. It's not a parabolic basin. It is something that just wanders off. Wherever it goes, we don't know. Now, we've heard a lot of talks about rational dynamics. And of course, in rational dynamics, there are no wandering domains, as Sullivan proved famously. But in transcendental dynamics, and in several complex variables, as a matter of fact, but in transcendental dynamics, in one variable, wandering domains do exist. And there are some well-known examples, beautiful examples, simple examples. If you haven't seen them, it's worth taking a look at them. I will give you a different argument. So if you haven't ever seen a construction of a wandering domain, if you learn nothing else from this talk, hopefully after this talk, you will know how to construct an entire function with a wandering domain. So I'm going to use approximation theory. It's not historically the first way that wandering domains were constructed, but it's the one that's relevant today. So for the purpose of this talk, I will just use one theorem of approximation theory, which is Aracelian's theorem, or rather a special case of Aracelian's theorem, the case of the plane. So Aracelian's theorem says essentially any holomorphic function can be approximated by entire functions. Well, if at all conceivable. So more formally, we take a closed set with the following properties: that the complement of this set together with infinity is connected. So this just means there are no bounded components. We don't separate the plane. And we also ask that it is locally connected at infinity. I'll ask you not to worry about that definition too much, because it will be clearly satisfied in all of our examples. You just have some nice sets, some finite union of nice sets. Actually, I would just have a finite union of strips or disks of things, or possibly a countable one which only accumulates at infinity. This condition will be automatically satisfied, but it is necessary. So suppose that we have such a set, and suppose that we have a continuous function on the set, which is holomorphic on the interior of A. Then we can approximate this function G arbitrarily closely by an entire function F. So for every epsilon, I can find a function F, entire function, which on A is epsilon close to G. Now you see, clearly we need all of these hypotheses. So if we're going to approximate arbitrarily closely by holomorphic functions, then we have to be holomorphic on the interior by Weierstrass's theorem. It's easy to see that we can't be separating the plane, because otherwise we'd be forced to have a pole or something like, put 1 over z minus zeta, where zeta is in this bounded component. We can't approximate that function closely without getting a residue. When you integrate around, we have to have a pole. And well, the final one about local connectivity, it's a similar reason, which I don't want to go into. But anyway, so the only thing really that you have to take from this is if we have such a nice set A, we have a function continuous on it, holomorphic on the interior, then we can approximate it by an entire function. Okay? Any questions about that? This is important. I will use this throughout the talk. It's important to understand. So the first use of approximation theory to construct wandering domains was by Eremenko and Behaviour in a paper, another fine paper of 1989. I will talk a little bit about what they did. So they didn't need to construct some wandering domain because some wandering domain already existed, but that's what I will start out with. I will show how to use Aracelian's theorem to construct a wandering domain. And then we'll just, by and by make the construction a little bit more complicated, and hopefully in the end you'll have an idea of how to construct a counterexample to Eremenko conjecture. But right now we just want to construct a wandering domain. So let's start with a union of disks, countable union of disks going out to infinity. So my goal is to make a wandering domain which contains each of these disks. So the wandering domain contains the disk D0, then the next one, image, contains the disk D1, and so on, going off. So how would I do this? Well, I make a function that does this, right? So I take a function g, which maps, say, D0 into this disk D1. For example, it just takes it all and maps it to the center, right? Constant map whose value is just the center of the disk D1 on the disk D0. On the disk D1, it's constant, center of the disk D2, and so on. So this is the first part of my model function. Now, if I approximate this with an entire function, right? So the radii of the disks, let's say, are 1. I approximate up to an error of 1/2. I will have a function that does the same thing, that maps this disk inside this disk, this disk inside that disk. No longer to a point, of course, but to something small. So I will have something which is in the Fatou set. D0 will be in the Fatou set, D1 will be in the Fatou set, D2 will be in the Fatou set. And it seems plausible it will be a wandering domain, but it could also be an invariant component, right? So it could somehow be that these disks all get connected together just as one component. We don't want that. We want a wandering domain. So how do we make sure that we get a wandering domain? There are many ways of doing this, but I'm going to suggest one, which is as follows. I'm going to add another disk, which is mapped to itself. So I create an attracting fixed point inside of here. So my approximating function will have this disk mapped inside itself. It will be in a periodic Fatou fixed invariant Fatou component, in fact. And it'll have an attracting fixed point, even though that doesn't really matter. Okay, and then I'm just going to map some things inside this disk. I'm going to take all of these lines, separate these disks, and each of them, I define my map G to map inside this disk, which is then mapped inside itself. So let's see, I still have a continuous function defined on the set A. The set A satisfies all the hypotheses of Aracelian's theorem. It's locally connected at infinity. You see, if I want to connect any large point to infinity, I just go along the corresponding strip, not causing any problems with that. I approximate this function sufficiently closely by an entire function, then these will all be in the Fatou set, going to infinity in the escaping set. These lines will not be in the escaping set, so they cannot be in the same Fatou component. They're mapping to this basin of attraction. And therefore, all of these Fatou components have to be different, and we have constructed a wandering by a very simple application of Aracelian's theorem. Any questions at this point? Once again, we're going to use this construction. We're going to make it more complicated. So if there are any questions about it, please ask now. Is it hard to prove Aracelian's theorem? It's not that hard to prove Aracelian's theorem. I mean, you use Runge's theorem. You start with Runge's theorem. Is it hard to prove Runge's theorem? It's not that hard to prove it. There's a textbook by Gaia which proves all of these theorems. I will refer you to the book by Gaia, but it's yeah. Actually, sorry, it's not Runge's theorem. It's Magellan's theorem, if you want, which is the version. So Runge's theorem requires that your map is analytic on a neighborhood of the set, whereas Magellan's theorem is the same for polynomials, approximating with polynomials. So that you don't require the map extends analytically beyond that. And then, when you take that to the entire case, you get Araceli. Okay, so note that the wandering domain I just constructed is in the escaping set. And you may think, oh, there's our connection with the escaping set. Well, it's actually not quite that simple, but it's an important observation. This wandering domain is in the escaping set. Now, one may ask, and this was a question, right? Is this always true? Because I mentioned there were other examples constructed by Baker, and there were examples of Hermann coming from lifts, and all of those had wandering domains where the iterates tended to infinity under iteration. So let us call a wandering domain in the escaping set an escaping wandering domain, and one that is not in the escaping set, but where the orbits are unbounded, an oscillating wandering domain. The idea it goes out and comes back. There's a potential third possibility, which I will not mention. We do not know whether this can occur. That's the case where the orbits remain bounded. For the oscillating ones, we do know that they exist. So this is one of those things that Eremenko and Ljubich constructed. In their 1989 paper, they use approximation theory to construct an entire function with an oscillating wandering domain. And how do they do it? Well, similarly as we did before, they build a partially defined function with the desired properties. But now the problem is that you have something which accumulates on some finite parts of the plane. So they can't use Aracelian's theorem exactly, or Runge's theorem exactly as it is. They use another suitable variation of the theorem, which allows them to get better control near these points where the wandering domain accumulates. So here's a picture from their paper, right? So they have this. So what happens in their example is that they have this domain, and it sort of maps. You have got this domain D0, and I guess the domain D0 maps inside D1, and then it maps out into this region here. It gets mapped back into this region D2. It maps out there. So in the end, it accumulates on the point 0, A1 in this orbit. And in order to construct this function, they need to approximate the function, make sure that the 0, A1, and so on get fixed, and the derivative is also controlled. So it's a little bit subtle. And I will change the point of view a little bit to give you a different construction of an oscillating wandering domain, which doesn't need this extra control. So this turns out to be a key idea. It's a simple idea, but it turns out to be a key idea in what we do, which is that instead of building one function and then throwing an approximation theorem at it and boom, getting our entire function in one step, we will actually build it in an inductive way. So we will build a sequence of n where our first function, it has some of the properties that we want, right? So we do something which has some initial, the right behavior on some initial series of iterates. And then we just approximate that function by an entire function. Then we build the next one by approximating our function f1 on a big set together with some extra properties where we change some extra places where we're changing it. And we keep doing this. And by making sure that every function fn plus 1 approximates fn on a large set, we'll get a convergent sequence of functions. And then this limit function is the one that we want. So the advantage of this is that we can use the properties of fn. We may not know exactly what fn does, but we may know qualitatively what it does. And we may use these properties of fn in defining our map, Gden plus 1. And I should say it's actually not, I mean, in a sense, this happens in the paper of Eremenko and Ljubich, but it happens in the proof of their special approximation theorem. Right? So that's how they prove their version of the approximation theorem. They apply Runge's theorem to get a sequence of maps and converge. But they sort of don't use it dynamically. So let me try, so that you get an idea of how it works. Let me give you a construction of oscillating wandering domains using this idea. And we will only use Aracelian's theorem. So in all of this, the only approximation theorem I will use is Aracelian's theorem. So what should my example look like? Here's the scheme of the general construction. I again have a disk, a sequence of disks going out to infinity. Within these disks, I'm going to pick two smaller disks within each. So I've got a disk S0, T0, S1, T1, S2, and T2. and so on. And what I want is I want to build a wandering domain that has the same kind of behavior as Eremenko and Lubitsch had it. I'm not going to prescribe where exactly they're going to accumulate, because that's going to change when I apply Aracelian's theorem. I can't say, oh yeah, I want them to accumulate at this point, but I don't have to. So what I want is a wandering domain that starts in T naught. Oh, sorry. So let me say this first. So throughout the construction, at every stage, the disks S, J, they are there in order to be moving up. So the disk S naught will just be mapped by an affine map to this bigger disk here. S1 will be mapped by an affine map to this bigger disk here. Now, if I approximate sufficiently closely, then the approximating function will do the same thing. It will map the disk S naught, or maybe a slightly smaller disk, conformally onto some disk that contains both the yellow and the blue disk. And well, then I'm going to have to modify what I'm doing in the disk Tj in order to get my example. So what I want is a domain that starts in T naught and then maps inside here. Or let's say we take the whole disk T naught, in this case maybe, and we map it inside this yellow disk in such a way that it maps up, and in the next step, it maps into the blue disk. And then it maps back down, whoops, back into this yellow disk, up, at a further step up here, maps back down, goes up, goes up, goes up, a further step. So that's the structure that I'm looking for. So let me say this again. So my wandering domain will start with this disk T naught. It will map inside S naught, then up into T1, back down into S naught, into S1, into T2, back down to S naught, S1, S2, then into T3, and so on. So that's the structure that I'm looking for. So how will I achieve this? Well, I'm going to stop sharing my screen for a moment so that hopefully this will record the board and everyone can see the board. So I have my disk here that I start out with, and I have my disk. I don't see the slides. So I have a blue disk, which is purple now, a yellow disk. And I will start with my map G naught, let's say. No, maybe it's G1. Call it G naught. It will just map this disk inside the blue disk, inside the yellow disk. Some point or some, well, maybe conformally. It'll map this disk conformally into some small disk here. And then I will map the yellow disk up onto this larger disk up here. Okay? So this is my map G naught. My map G naught does what I wanted it to, and I approximate by a map F naught. So the map F naught does the same thing, right? So the map F naught is now an entire function, and it maps this disk inside here conformally, and it maps this conformally onto, well, maybe not quite this disk, but onto a slightly smaller disk. It covers the purple disk and the yellow disk. Which means that under F naught, there is something inside of here which maps onto this disk here, which is T1. Right? So this is T1. This is S1. So S naught contains a pre-image of T1 under the map F naught. So far, so good? Wherever this is. I'm going to blow up S naught. Let me just blow up S naught. So this is S naught. So S naught already has the image of G naught inside of there. And somewhere in S naught, I also have this pre-image of this disk, T1. Is it T1? No, it's not T1 that I want, is it? It's sorry, now I've managed to confuse myself. So I want to map this disk. I map this disk inside here. I'm mapping up here. So what I want to make sure is that at the next step, I am mapping out. Sorry, so I made a mistake. I made a mistake. Let me start again. I got my map. I got mixed up. So we have this. We have the disk. We have the map G0, which maps the yellow disk onto this bigger disk. So under the map G0, I'm sorry, very sorry. Under the map G0, there's a preimage of T1 inside this disk. Okay. This is here. This is G0 inverse of T1. So what I can do is I can say, let me map this disk. Let me define G0 on this disk so that I'm mapping inside this preimage. Right? So what will happen is that now my map G0 maps the purple disk inside this little component here, which then gets mapped up onto T1. So in other words, this purple disk under 2 iterates of G0 will map inside here, and it will map into T1. Sorry about that. I hope this didn't cause confusion. So that's the map G0. Our map G0 has the right property, exactly what I want, for the first 2 iterates. After that, you know, well, iterates aren't really defined. I haven't really said what G0 should do on here, but it doesn't matter. So now approximate with my map F0, and it will do the same thing. So it will map this disk inside here and back up inside there. So now what do I do? Well, now I define my map G1 to take the disk S1 onto this disk up here, which has a T2 and an S2 inside. So therefore, so G1 agrees with F0 on this disk, and on S1 it maps conformally up to here by an affine map. In particular, there is a preimage of T1 inside S1, which then has a preimage inside S0. Right? So this is G1 minus 2 of T2. So now I define my map G1 to map this thing inside that one. Okay, so to recap, what does my map G1 do? It maps the disk T0 inside S0 and then inside T1, because that's how I chose my map F0 to begin with. Then it maps the disk T1 inside S0 up into S1 and up here, which is what I want. And again, this will all be preserved under approximation because I have space, right? So I approximate with a close enough map. All this behavior will be the same. And therefore, I can approximate using Aracelian's theorem by a map F1. And this way I continue. I will build a map F2, which will now agree with F1 on, let's say, a big disk containing these first 2 disks. F3 will agree with F2 on a disk, well, not agree, but be very, very close to it on a bigger disk. Now, if I make those errors that I use shrink geometrically, then overall my functions will converge uniformly, well, locally uniformly on the complex plane. And therefore, I will get an entire function in the limit that has the same behavior. So I'm sorry for the slight confusion. So let me recap. We built a function that has the right behavior for the first few steps. Then we built another function which agrees with our map F0 on some part of the disk, well, again, up to a very small error, and now gets the right behavior for an extra few steps. We approximate that one. We only have a change on these disks Tn, really, what's been done before. So we don't, well, and on the disks Sn, but they go off to infinity. So we never have to change somewhere that we've already dealt with. And the limit, we'll get a wandering domain that has this behavior and therefore is oscillating. We don't know where it accumulates within the disk S0, I mean, it will be the nested intersection of the pullbacks of these disks. Wherever it is, they will shrink down to a point. That's where it accumulates. We don't know what that point is, and we don't care, right? Because at every stage, we can use the behavior of the function that we had before. So that's quite a simple construction, if you don't mess it up, of a oscillating wandering domain. Okay. So I said we were working on a different problem when we realized we could solve Eremenko's conjecture. So this problem related to the behavior of boundary points of wandering domain. Ah, thank you, thank you. There we are. Let's share the screen. So the question that we were thinking about is one that was asked by Phil Rippon. So the question was the following: can the escaping set contain a bounded wandering domain whose boundary does not contain any escaping point? So in the ones that we constructed, the wandering domains, their spherical diameter shrinks to 0. So if they go to infinity, all the boundary points also go to infinity. Sorry, that's not the question, but there's the first question I will start out. So if they go to infinity, then all the boundary points go to infinity. If they're oscillating, then all the boundary points will also be oscillating. So let's start by asking, can the escaping set contain a bounded wandering domain whose boundary does not contain any escaping points? Now that's why is this question relevant? Well, if this could happen, then we'd have a bounded component of the escaping set. So one could ask, is this a way to resolve Eremenko's conjecture? And well, Phil and Gwyneth considered this question, and they proved that this cannot happen. So if we have any wandering domain, then the boundary must have a full harmonic measure set of points that also go to infinity. And actually, you already knew that this thing couldn't happen because I told you that the escaping set union infinity is connected. And this is how they prove it. This was the thing that was needed. So this is the question of Phil Rippon. The question was, well, so they prove it has full harmonic measure, but actually in all the examples that were known, every boundary point was in the escaping set. So the question is, can you make such a wandering domain where the boundary is not completely contained in the escaping set? And we can ask the same question for oscillating wandering domains. If we have a bounded or unbounded oscillating wandering domain, is the boundary of the escaping set, can the boundary of the escaping set ever contain an escaping point? So we were thinking about this question, but the answer also gives an answer to this question. So how would we go about constructing such a domain? So the problem now is with this construction, well, everything's bounded. So we're only ever going to get things where the spherical diameter goes to 0. So now I only have a few minutes left. So let me try and give a quick idea of how we resolve this question. So we use the same kind of picture. We want to use the same kind of picture, but what we need is we need something unbounded, right? So we need the wandering domain. When it comes back to the finite part of the plane, you want point in the wandering domain to come back to a bounded part of the plane, but some points on the boundary to continue to go towards infinity. So your spherical diameter has to be allowed to get bigger, or at least to remain big. So how do we do that? Well, we use the same kind of construction, but now we use strips instead of disks. And I need to use an eraser. Actually, maybe not. I have another board. Here we are. Okay, so let's replace our disks by strips. Well, let me talk on the slide for a moment, and then I will move to the board again. So we use the map Z maps to 5Z, just for simplicity. So this will map the strip S0, which goes from imaginary part 1 and 2, to this bigger strip, which goes to 5 to 10. Inside it again, we have a strip S1 and a strip S2, T1. The same map that maps to 5Z will map the strip S1 to this bigger strip up here containing these two domains. So this will be our scaffolding. This will be how we map things upwards. So what we'll be looking for, and actually I will draw on this slide, I think. what we'll be looking for is, again, a wandering domain that starts out in T0, right? And then it maps down into S0. So we're in T0, we've got some, let's say, red point, which should be in the wandering domain, and we'll want to have a green point, which is end up being on the boundary. So what we want is we want to map down into S0 in such a way that the red point goes back to a bounded part of the plane. Whereas the green boundary point ends up being, actually, let me draw it to a different place, because this is not how we will do the construction. And instead, I've lost my black pen. Okay, so yeah, I'm trying to. Here we are. This will work. Hopefully, this will work. So what I will do is I will map in such a way that this green boundary point goes far to the left. Interesting behavior. Okay, and my red point. It was oscillating, indeed. Very, very good. Yes. Okay, so we're mapping inside here, right? But inside the preimage, so this strip S1, like I already said, this one is going to be mapped over this whole strip, right? So we map inside the preimage of this strip T1, just like we did previously. We map this inside the preimage of the strip T1, so this thing now gets mapped up inside T1. And then it gets mapped down. And actually, I don't think I have no time. So I will not try and give any more details, except to say it's the same proof, right? I just use a different map to go from here to there. Just use some conformal map that maps this in the way that I want. Okay, so the final ingredient, and I'm almost at the end. The final ingredient is, well, how do I ensure that this escaping point is actually on the boundary? And well, there are different ways of doing this, and we had a different way of doing it. But then we realized there was a similar construction of Bochtala using very similar ideas as this approximation, which allowed him to realize a bunch of simply connected domains exactly as wandering domains of entire functions. And I won't talk about this because A, there's no time, and B, there's a talk about it right after this. So we can use a similar approach to actually make sure that our wandering domain in the end is an exact half strip, and around it, much as those lines that we had before, there are a bunch of lines. So this half strip will be the wandering domain, and around it there will be a bunch of things which get mapped inside this disk, which gets mapped inside itself. So they are not in the escaping set. And then we get the example that I promised you. In fact, I should say it's an example because there are many different ways of making examples. The one in the paper is a bit different. So take this half strip. Then we show by this method that there exists an entire function with the following properties. So this domain U is an oscillating wandering domain of that. The points inside come back to the bounded part of the plane infinitely often. The boundary point 0 is in the escaping set. So this is the point. Every time we come back to this strip S0, we actually map to the left quite a bit. So this point actually goes to infinity. And furthermore, there are all these bits outside which are in the Fatou set, and not in the Fatou set, but in the bounded orbit Fatou set, in an attracting basin. So the closure of U actually is a connected component of the set of points with unbounded orbits. Now, similarly as before, and again, David will say more about this, I think, the escaping set on the boundary of an oscillating wandering domain always has 0 harmonic measure. So most of the points on the boundary of this strip are not in the escaping set. So what about this point 0? This point 0 is in the escaping set. It can't be connected to anything outside of these curves because the points in here have bounded orbits. So there's no connected shape in the escaping set going to infinity intersecting these. But this thing is also not in the escaping set. And the boundary contains a dense set of points not in the escaping set. So there's no way of connecting this point outwards to infinity. And therefore, this is a point connected component of the escaping set. And I have no time to mention further results, but happily, I don't have to, because someone else will. So I think here I will end, and I will say dziękuję, and thank you for your attention.
Thank you very much. Any questions? Yes.
Okay, thank you for your nice talk. So the question would be, do you have any idea, or is it possible to control in your constructions using Archimedes theorem to control the class of functions in which you are working, or you come up with something completely exotic, you don't know it's bounded or something?
There's no way to control the class of functions when we're working with Archimedes theorem. Now, of course, there's a natural question whether you can do this example with a bounded set of singular values, let's say, or even a finite set of singular values. So the difficulties, well, the one difficulty, as I said, was what kind of structure would this example have to have? Now, actually, the sort of general structure of our example, I think in principle could be realized within the class S. Certainly in the class B, possibly in the class S. That's not the too bold here. But then you still have this issue of you really have to control extremely well how you would build such a function. Now, of course, we do have the methods of Chris Bishop, and we do want to talk to him. I mean, I think we need more than we have at the moment. But it's a very good question. So I mean, I believe before that Eremenko's conjecture would not be true in the class B, and I believe it even more now. But to build an example, it will require some more work, definitely, some new ideas about the control of the function.
Thank you.
Thank you. So today is the last day, so I think we should try to stay on schedule. So maybe we can just postpone other questions either to coffee break or to email, because
just a short comment. This Banach Center publications 84, in fact, was after a semester in Banach Center in 86. And Eremenko participated, but he arrived after, by formal reasons, he arrived just when the semester finished. Nevertheless, it was very, very useful stay of Eremenko and Warsaw at that time.
Okay, so let's just thank Rempe again.